All right, today we're diving deep into the engineering battle plan, a plan that plays out every single day between our tallest buildings and, well, the relentless force of the wind. I mean, have you ever stood at the bottom of a skyscraper on a really windy day? You can sometimes feel it sway, just a tiny bit. And it makes you wonder, right? What in the world is stopping this giant thing from just blowing over? Well, spoiler alert, it's not magic. It's actually an incredibly detailed engineering battle plan. We're talking about a strategy where every single gust of wind is anticipated, every pressure point is mapped out, and every piece of the structure is part of this calculated defense. So yeah, let's get into it. Okay, so just like any good battle, the first phase is all about reconnaissance. You can't design a defense until you've gathered some serious intel on your own structure and, of course, the environment is going to face.
Seriously, you can think of it just like a general assessing their troops and mapping out the battlefield. For a structural engineer, though, the troops are the building's materials, and the battlefield is its location. It all comes down to collecting very, very specific data.
So this is basically what that intelligence report looks like. And it's all guided by super detailed standards. In this case, the Bangladesh National Building Code. Engineers have to answer a whole list of questions. Where is this building? What's it for? Is it just an office or is it something essential like a hospital? How tall is it? What does the surrounding terrain even look like? Every single one of those answers is a critical piece of the puzzle. And you know what? It all starts with one key number, the basic wind speed, which they just call V. Now, this isn't your average, everyday wind speed. No, this is a very specific, super powerful 3-second gust that's measured at 10 meters up, and it has a really low chance of ever being topped. This is the baseline, the raw power of the enemy, if you will. It's the fundamental threat that every other calculation is based on. But that basic wind speed, that's just the starting line. From there, engineers have to calculate something called velocity pressure, or QZ. And here's the really crucial part to get. Wind isn't some uniform force. It actually gets way stronger the higher up you go. So this QZ value is what turns that one single wind speed into a dynamic pressure that literally grows as the building gets taller. And this chart, it shows you that exact point perfectly. Look, down at the ground floor, the pressure is pretty low. But by the time you get all the way up to the rooftop of a tall building, oh man, the wind is pushing so much harder. This is exactly why you feel the most sway on the top floors of a skyscraper on a windy day. Okay, so now the engineers know the overall force they're dealing with. The next step in the battle plan is to map out exactly how that force is going to attack the building. And trust me, this is where things get really interesting and pretty complex. A lot of people think that wind just pushes flat against one side of a building, but that's not how it works at all. In reality, as the air flows around a structure, it creates this incredibly complex pattern. You get high-pressure zones where it's pushing, sure, but you also get low-pressure zones where it's literally pulling on the building. It's creating suction. So to handle all that complexity, engineering codes, like the one you see right here, break the building's surface down into different zones. You can see them labeled 1, 2, and 3. Now, zone 1, that's the main face. But the real action, that happens in zones 2 and 3. We're talking the edges and the corners. This is where the wind just whips around and creates these intense suction forces that can actually be stronger than the direct push on the front. And how do they put a number on the force in each of those zones? Well, they use something called the external pressure coefficient, or CP for short. The easiest way to think about it is just as a multiplier. For every single zone on that building, there's a specific CP value, and it tells you exactly how much of that velocity pressure, remember that from before, gets applied as either a push or a pull. So let's break that down a bit more. The windward face, that's the side the wind hits head-on, it gets positive pressure. It's being pushed in. But then on the sides and the leeward face, that's the back, the airflow creates a kind of vacuum. That's negative pressure, or suction. The building is literally being pulled outwards. And that suction can be just as powerful, sometimes even more powerful than the direct push. And this isn't just some theory, by the way. It's written right into the rule book. Major standards like ASCE 705 state it plain as day. Those little plus and minus signs, that's literally the language engineers use to describe if the wind is pushing toward or pulling away from the building's skin. Okay, so to get the final design pressure, engineers have to combine all these different forces. They take into account the external pushes and pulls. They even consider what would happen to the internal pressure if a window broke. And then they add one last absolutely critical ingredient, the gust effect factor. This is what accounts for the wild, chaotic nature of wind, making sure the building can handle not just a steady force, but those sudden, violent gusts. All right, we've gathered our intel, we've mapped the enemy's attack. Now it's time for the final phase, building the defense. This is the moment where all those abstract numbers and pressure calculations get translated into the real-world steel and concrete that are going to keep the building standing tall. And this whole process is super methodical. First, engineers use all those pressures to figure out the total wind force on each and every floor. Then, they apply those forces to a digital model of the building skeleton. After that, they run a whole battery of rigorous safety checks, and only then do they finalize the design for every single beam, column, and foundation to make sure it's strong enough. Now, the real hero of this whole story is something called the Main Wind Force Resisting System, or MWFRS for short. And this isn't just one single thing. It's the entire structural skeleton of the building, all designed to work as a team. We're talking columns, beams, massive concrete shear walls, all of it forming one cohesive system to take all that wind force and channel it safely down into the ground. But of course, buildings don't just have to fight the wind, right? They also have to hold up their own weight. That's the dead load, plus the weight of all of us and our stuff. That's the live load. So codes like this one provide specific load combinations. Engineers have to test the structure against all these different worst-case scenarios, like what happens when you combine the building's full weight with a massive windstorm. They have to make sure it can handle everything at once. And believe me, these safety checks are absolutely non-negotiable. The engineers are asking a whole bunch of critical questions. Is this building going to tip over like a domino? That's the overturning check. Is it going to sway so much that people get uncomfortable or the walls crack? That's called story drift. Every single part of the building's defense gets put through its paces, tested for both strength and stability. So just think about that whole journey for a second. It all starts with one single number, that basic wind speed. And from that one number, engineers build this incredibly detailed blueprint of all these invisible forces that are attacking the building. They essentially make the unseen seen. And it's this meticulous battle plan, one that's guided by decades and decades of research packed into these engineering codes, that's ultimately what keeps us safe. It's what allows us to build higher than ever before and to live and work safely inside, even when the wind is just raging outside. But, this battle is never really over, and it leaves us with a really critical question for the future. As our climate continues to change and as storms get more frequent and way more intense, how is this engineering playbook, this battle plan, going to have to evolve to make sure our cities keep standing?